I'm going to cover Miller indices, or the Miller index, that you're seeing this kind of notation in parentheses or brackets in your textbook, and several students have been asking questions about that, so I want everyone to hear a little bit about it. And I'll also talk about the different crystal systems of the minerals that you're learning. The Miller index is this notation in parentheses 111 in this example, or it might be 201 or 001. Those relate to the unit cell in a crystallographic axis. And so in this diagram, you're seeing three axes. You're seeing X, Y, and Z axis. And those correspond to the A axis, or the short axis, an intermediate axis, that's the B axis, or the long axis in a crystal, that's the C axis. And the Miller index relates to units away from the origin point of those axes. So from this center point here, we'll measure units out to determine the Miller index. You measure the units out, and in this case, we're determining the Miller index for this plane here. It is at an angle. It intersects the C-axis at 1 unit away, the A-axis at 1 unit away, the B-axis at 1 unit away. Okay? You take the reciprocal of those numbers, so down here, 1 over 1 for all 3 axes, for the A, B, and C axis. And then you clear the fraction, and you end up with the Miller index of 111. This is a simple example. Another example is this sort of plane, and what we're looking at is a plane that intersects the A and C axis 1 unit away, but is parallel to the Y axis. It never intersects. And so the intercept length for the A axis is 1, the B axis is infinity, and for the C axis is 1 also. You take the reciprocal of those values and you clear the fractions, you get 101 for that Miller index. Here's a slightly more complicated example of a Miller index, and that is on the left here. We have 2 planes that have the same Miller index. They're just oriented in a couple of different ways to help you see what the Miller index should be. Let's just look at this plane for now, and you'll see that the plane intersects the C-axis half as far away from the origin as along the A-axis, and that the plane is parallel to the B-axis. So we'll call the distance away from the origin that this plane intersects on the A-axis, this point, we'll call that 1 unit. And that means that the plane intersects the C-axis half as far away. So the intercept length there is 1 for the A-axis, half for the C-axis, and infinity for the B-axis because it is parallel to the B-axis. You take the reciprocal of those values, and you get a Miller index of 102. Here's another example. In this case, plane A is oriented the same as in the last example, with the plane intersecting the C-axis half as far away from the origin as the A-axis. So we'll look at plane B, and that's the opposite case, where the plane is intersecting the A-axis half as far away as it is along the C-axis. So we get intercept lengths of 1/2 for the A-axis, infinity for the B-axis because it's still parallel to the B-axis, and 1 for the C-axis. Take the reciprocal, and then you get the Miller index of 201. So notice the notation. The Miller index notation uses 3 numbers and sometimes 4 numbers in parentheses. It will always be 3 numbers that are called H, K, and L for all of the crystal systems except for the hexagonal crystal system, which will have 4 values. Now, when you see this in your text, you'll see the same numbers, the same HKL values, but they'll be in the brackets. And that's what's used to describe the cleavage planes. So just note the distinction. Now the crystal systems, we've looked at this a little bit before, but I haven't really talked in great detail about them. There are 6 main crystal systems, and you'll see that the names of the crystal systems are over here on the left. We have cubic, tetragonal, hexagonal, orthorhombic, monoclinic, and triclinic. And there are these A, B, and C axes that represent the crystallographic axes in the minerals. And then some information on the right-hand side that tells you something about the length of the different crystallographic axes and the angles between those different crystallographic axes. Let's look a little bit more closely. Here are the first 3, the cubic, tetragonal, and hexagonal crystal systems. The cubic crystal system, as in fluorite, has the 3 crystallographic axes are all the same length, so that's why this says that A equals B equals C. And all those angles are, the angles between those crystal axes are 90 degrees. That describes a cube, hence the crystal system name of cubic. The tetragonal crystal system, as in rutile, the A and B axes are the same length, but the C axis is different, and all the angles between those axes is 90 degrees. In the hexagonal crystal system, this uses the example of beryl, also quartz is hexagonal. The A and B axes are the same length, and in this case there are 3 shorter axes. So really it should be, it's often noted A1, A2, and A3. Those are all the same length, but the C axis is a different length. And the angles are either 120 or 90 degrees to one another. The next 3, the orthorhombic, monoclinic, and triclinic crystal systems, instantize an example of an orthorhombic crystal system. And it's also an orthopyroxene, if that helps you remember in the future. The 3 crystallographic axes are all different lengths, but they all intersect at 90 degrees. The monoclinic crystal system, this is the last 2, the monoclinic and the triclinic crystal systems, are the crystal systems for feldspars. Monoclinic minerals, none of the 3 crystallographic axes are the same length, but the angle between the C and the B axis is given the notation alpha, and the angle between the A and the B axis is given the notation gamma. Those angles are 90 degrees, but the angle between the B and the C axis, that's given the notation beta, that's not 90 degrees. The triclinic crystal system, none of the crystallographic axes are the same length, and none of the angles between those different axes equals 90 degrees. So what you learned in this module is that Miller indices can be used to describe the orientation of the cleavage or twin planes in minerals that you're learning. The crystal systems tell you about the relative length of the crystallographic axes and the angles between those axes. And the crystal systems are related to the number of optic axes in a crystal. And that's why I had labeled biaxial, uniaxial next to those crystal systems. And that all can be used together to understand the information that's in your text or in your reference book to find the right physical or optical properties in the minerals that you're looking at. So please apply this information in your labs as you learn to identify minerals.